So we start a new chapter now. Chapter 7, Ising or Ising. It depends how you read it. Oh no, it's not Ising. Sorry. It's Metropolis. Sorry. It's Metropolis. We start with Ising model or Ising model. So some of you probably do know what is Ising model. Some of you probably don't know. So let's start by talking about it. So Ising model is a simple model of magnetization. Let me start like that. So basically, imagine two spins. They have ferromagnetic interaction. Okay. We write its energy or Hamiltonian like this. So let's say this is S1, this is S2, minus J, this is coupling, times S1 times S2. So why this works? Because if they are both, so these can be plus or minus 1, right? Plus or minus 1. They can be up, both down, one up, one down, one up, one down. So if they are both up, the energy of the system is minus J. Both down, energy is minus J. Yes? Up, down, plus J. Down, up, plus J. Now, if J is positive, then you have a ferromagnet, right? Because if J is positive, aligning decreases the energy, so the ground state is when spins are aligned, right? If J is negative, then it's anti-ferromagnetic or antiferromagnetic. Okay, so far so good? Any questions? No. Good. Now, you can also add magnetic field to this. For example, you can write Hamiltonian to be minus J times S1 times S2, right? But you also apply magnetic field, let's say. Then you have B times S1 minus B times S2. So if magnetic field is, let's say, 1, let's say magnetic field is plus 2, let's say. Then what is the energy of up? Minus J minus B times, minus B, so minus 2. Okay, let me go with just B being larger than 0. B is greater than 0. J minus B, so the energy is minus J minus 2B. So down, minus J plus 2B. Which one is lower in energy? If B is positive, is this one more favorable or this one more favorable? The down one is minus J plus 2B. The up one is minus J minus 2B. Lower energy is up. So I apply up magnetic field, so I give an extra tendency of looking up, okay? We started simple, but it will be crazy complicated. Don't worry about that, okay? Very, very soon. Now, how can it be a model of magnetization? Let me tell you. Even now we see something going on, even with two spins. Look, up, up, forget about magnetic field, up, 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 down, down, up, and down, down. This has energy of minus J, this has plus J, minus J. Let me also talk about magnetization. Let me say magnetization. This is the average of spins. Like, what is the average of all the spins? So we have two spins. If they are both aligned up, then the magnetization is 1. If one is up, the other one is down, the average is 0. This is 0. This is minus 1. This is magnetization, okay? Do you have any question at this point? Any questions at all? So you see that you have a magnet here, you have a magnet here, you don't have a magnet here. Okay? Now, if we also put in the system temperature, okay? Now let's include temperature in the system. What is the probability of this, each one of these states? Probability. Probability of this one will be what? Do you remember how probability was proportional to e to the minus energy over kBT? Do you remember this? Everyone? Now, let's define something called partition function. It's shown by z. I'm going to write it down as sum of all possible states, all possible possibilities. Sum of all possibilities e to the minus ei over kBt. For every possibility, up, up, down, down, up, down, down. Now this is the total function. But each one of them has a particular probability, right? Each one of them has e to the minus j over kBt over z. This one has e to the plus j over kBt over z. This one has e to the plus j kBt over z, e to the minus j over kBt over z. What does it tell you? When I change the temperature, what happens to the system? When I increase the temperature, what happens to these probabilities? Let's say temperature is almost infinite. Okay? What happens to these systems? You are thinking, right? When t goes to infinity, you get the same value in each one of them, right? It's e to the 0. And sum of e to the zeros is, so z is going to be 4. So each one will have 1 over 4 probability. When z is infinite, right, everything is possible. While when z is very low, what happens when z is very low? Sorry, t. Very good. When t is very low, do you see that these probabilities will go up? These probabilities will go down? Do you see that? So while we decrease the temperature, spins want to get aligned, right? That's why you have a magnet at a certain temperature, and if you increase the temperature of the magnet, it becomes paramagnetic. It loses its magnetization, right? It's a war between order and disorder, okay? So this J, let's say J, It's all about free energy equals to U minus Ts. Okay? So this is the minus J S1, S2 stuff, minus B times S. Let me put some sums here. Si, Sj, I is not equal to J, etc. But this part is coming from entropy. Right? As you increase the temperature, the disordered part starts winning. So this is the order part. This is the disorder part. Okay. So let me summarize what we have seen so far. So what I have told you is this: energy of a certain configuration is minus J times sum over spins Si, Sj. I is not equal to J, right? Maybe I should write I greater than J. So we only look at it once. Minus magnetic field times Si over all I. And I'm going to even give you a system. I'm going to give you just a spin chain, Ising chain, one-dimensional. So we know who is interacting with whom. So this is 0 spin, first, second, third, etc. And this is interacting with that one, this is interacting with that one, this is interacting with that one, etc. Let's say we have n spins, and the last one is interacting with the first one. Okay? Let's say I give you particular number of spins. Let me give you 16 spins because I already have a code for it. Okay? How would you find the probability of a certain state? How would you find the probability of a certain state? For example, probability of everything being up is what? I give you J, I give you B, I give you KBT. Let's take B to be 0. For this case, B is 0, let's say. You only have J. Are you following? Yes? So what is the advantage of being all aligned upwards? What is the advantage? Let me answer my question. The advantage is to have lower energy. What is the disadvantage? Minimum entropy, right? You are alone. There is only one of you. You have very low energy, right? The probability, hence the probability is increased. But then there is only just one state that has that property. Then just flip one spin. How many of such states do we have? 16 such states, right? The first one could be flipped, second one could be flipped, right? What is the disadvantage? We lose a little bit of that energy favorability, right? So what I'm going to do is the following. I'm going to change KBT. Okay, let's say I'm going to take it from 0.1 all the way to 4 in the code. And I'm going to look at every possibility, and I'm going to calculate Z for every possibility. Do I calculate Z for every possibility? Let me see really quickly. Let me just put it here. Yes, I do. I do it over here. I can actually show you already the code. So I'm going to change the temperature. Apparently, I'm changing it from 0.2 all the way to 2. In the meantime, I'm going over all the possible 2 to the n states. There can be 2 to the 16 states, right? Up, 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 down, up, 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 no, down, up, etc. Right? You get it. You get it. I go over every one of them, and basically this one is creating this line here, although it seems complicated. It's basically creating binary and then turning it into a spin configuration. Okay, so it's basically, I'm going from 0 to 2 to the power of n minus 1, all the numbers, and the first number 0 is 0, 0, 0, 0, 0, 0, 0, right? And I write 0, 0, 0 as minus 1, minus 1, minus 1, minus 1. Then the first number is 0, 0, 0, 1, right? And it's turned into minus 1, minus 1, minus 1, plus 1 at the end. Did you get it? No? Where are you? Yes. Thank you. Thank you. Thank you very much. So let me just explain it. So S goes from 0 all the way to 2 to the 16 minus 1. So far, so good? When S is 0, I turn it into binary, and it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 zeros. And I turn it into minus 1, minus 1, minus 1, dot, 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 minus 1, minus 1. Okay? This is the first 0th state. Okay? Are you with me? When S is 1, it's the same thing except for 1 at the end. And I turn it into minus 1, dot, 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 minus 1, 1. I just turn zeros to minus 1 and 1s remain. So far, so good? So I have all the possibilities. And for each possibility, can you tell me what this line is doing? Should I increase the font? Do you remember what this one was doing? It was rolling, right? Shifting it. So what it is doing is, for each state, let's say you have minus 1, 0, minus 1, minus 1, dot, 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 dot. So it shifts it, minus 1, minus 1, 0, minus 1, etc., and multiplies each one of these, which corresponds to multiplication between the neighbors. Does it make sense? So you get the total energy from there, minus J times Si times its neighbor. Good? Then what this one is doing, total magnetization. It's summing the spins and finds you the magnetization, right? Then what is this one is doing? Let me tell you what Nk is. Nk is for a certain temperature. It's putting a certain magnetization into place. So basically, the magnetization can start from being minus 16. It could be minus 14. It could be minus 12. Dot, 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 12, 14, 16. Do you agree? It divides it by 2 so that it's minus 8, minus 7, minus 6, dot, 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 and divides by 2. Before dividing by 2, it adds 16, so that it starts from, this becomes 0, this becomes 1, this becomes 2, dot, 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 dot. Good? Until this is 16. So every magnetization corresponds to a certain probability value. So what it is doing is it's adding the probability of that state by finding e to the minus e over kBt. Okay. And finally, it divides by total probabilities. This is basically our, what was the name? Partition function. This is our z. Do you have any questions at this point? So let's run it. I'm running it. At the beginning, it seems like at low temperatures, these two edges of being magnetized completely down or being magnetized completely up, the two edges here are winning. It seems like that. But then as the temperature increases, the disorder wins. Did you get it? So at low temperature, okay, it hasn't finished yet. Let's let it finish. So at low temperatures, it's either negatively or positively magnetized. At higher temperatures, the magnetization is gone. Okay? Do you have any questions at this point? No questions at all? Yes?
What are the units for this temperature range?
Units? Do you mean like Kelvin and that kind of thing? Very good question. The bottom part is kBT over J. Okay, it depends on J. If J is 1 eV, then kBT is correspondingly changing. So it's really a model which applies to any J. That's a very good question. Any other questions? Well, it seems like if we decrease the chain, if we decrease the temperature of the chain, it will go to ordered state. Well, it's only 16 chains, right? And if we want to add one more, we have to double the calculation. Add one more, double the calculation. Add one more. Like if you want to get 100 chains, 2 to the 100 possibilities, right? So we can't do that. But let me just tell you that if you take this chain to infinity, this thing disappears. Actually, what happens is that no matter what the temperature is, disorder wins in a chain. If you have a chain, you can't have a magnet. If you have a 1D chain, you can't have a magnet. Good? But how about 2D chain, 2D system of magnets, right? Let's look at that one as well. Are you still with me? Yes? This time I'm going to take those 16 spins and put them down like this. I mean, this is just the arrangement, just to show you the arrangement. So I have these spins, the same 16, right? And again, there is a periodic boundary condition. So this one is connected to that one, and this one is connected to that one. Okay, there are connections in between, up, down. So what has changed when we moved from 1D to 2D? Was it beneficial to the ordered side or the disordered side? Do you understand my question? Who benefited from going from 1D to 2D? Interesting. Why do you say disorder? Disorder, it's the same disorder. It's the same. So when you talk about disorder, it's how many different combinations result with the same magnetization. So it doesn't matter whether they are arranged in a chain or in a 2D. You are going to sum up the spins. So disorder side actually is not affected at all. However, the order side is more powerful now. Why? Because before you had one chain and two neighbors, okay, which wanted to align them, right? So in the order side. Now you have one chain and there are 4 neighbors, right? So order is more powerful now. Remember that disorder 1 in 1D, no matter what the temperature is? Well, it's not going to be the same with 2D. In 2D, it's a fair fight. And this is our program for the 2D. What is different here? Do you see the same code? What is different is the way we calculate energy. So can you explain me this part of the code? Oh, before going there, I actually changed also something in this line. Do you see the reshape L by L? So before I had 16 chains, now I reshape it into 4 by 4. That's one change. The other change is this one. S times NP roll S with 1 in axis 0, S times NP roll S with 1 in axis 1. What does it mean? Exactly. So I multiply, I shift to the left and multiply. So I take care of these interactions. Then I shift up and multiply. I take care of those interactions. Yes? Good? This is the energy, and the rest of the code is the same. You will see there is a fundamental difference in how this one behaves. The other one had probabilities spikes at the edges, but the middle part was always like this, like a hump. I don't know if you remember it. But this one is a well. So it's telling you that the edges really win. I mean, the middle part doesn't even have a hump. Okay, the edges really win at low temperatures. But then what happens? There are these 2 peaks that come close to each other and combine into hump. Did you see what happened? Did you care? Okay. So what we saw here is this. We started with this probability distribution, then it went into this probability distribution, and then it went to this probability distribution, and eventually it came down to here. Okay, so if you trace the top parts, the magnetization, as you increase the temperature, the magnetization goes through these stages. So at low temperature, so let me call this low temperature, and this is high temperature. Okay, at low temperature you have a magnet, at high temperature you lose that magnetization completely. Do you have any questions? You don't have any questions? So who won this battle? It depends what the temperature is, right? So let me just draw you another picture. No, let me draw it. So this is the temperature. And there is some point here. Let me call it T critical, which is close to J over KB. Close. I mean, like, we will find the numbers. They will be like 2, 1.6, 3.5, but not like 10 to the 20. Okay? It's like a number times J over KB. So you have magnetization on this side, and then it will actually suddenly go down to 0. Okay? So we will have disordered part here, and ordered part here. And this will be critical part, criticality. This will be all about criticality. So what is interesting here is that although we have just numbers, right? E to the minus something, e to the that, e to the this, but what we get is non-analytic here. Non-analytical behavior as n goes to infinity. As you increase the number of spins, this becomes, what we see here is rather smooth, right? Do you see? We have something like smooth here. But as you increase the number of spins, it will become very sharp transition. Do you have any questions? Yes?
What is non-analytical behavior?
It is when you don't have the derivative. Köşeli. Like it comes like this, and it doesn't go like this. It actually goes like this, suddenly increasing. And we will get some feeling about why this is happening. Okay? All right. Do you have any questions at this point? No? Somehow I've lost my ability of teaching and getting people excited, but this is a really exciting subject. Let me show you some stuff. Yes?
How the heat map, like,
Yeah.
in the heat map of previous one, we had same data points, and it is like 2D one. But in the 2D one, should we have much more data points? Did you get a slice of it? Like
No. It's the same thing because you still have 16 spins. Okay.
The way they arrange things.
The way they arrange. This is not the spins themselves. This is, I should put some labels here. This is kBt over J versus magnetization. And even these numbers are wrong. This should be 0 and this should be plus 16, minus 16. Sorry about that. But I have better pictures later. So, it's a very nice problem. The problem is very well defined and it has physical consequences. It's perfect for a physicist who doesn't like to go out. Okay, like if I solve this at home, it will be relevant outside, and it's a clean, like perfect for an obsessive compulsive kind of a person. Like it doesn't have this nature in it. It's just mathematics. Okay, no dust, no clean room needed. You just need to solve this problem. Well, I'm not trying to say that who solved it was like this, but there is a person who solved this problem for 2D model. Let's look at that paper. This guy. He got a Nobel Prize for something else, but this is his paper, Crystal Statistics, a two-dimensional model with an order-disorder transition. And how many pages? 33 pages. And okay, very nice paper. There is a famous series of books by Landau and Lifshitz. Have you heard of that? Yes. It's a legendary series of books, and they usually present everything very shortly. Like, you can show that this is the case, but the proof is 30 pages or whatnot. So I didn't check this, but I've heard that this takes 7 pages in that book. It's a huge thing. This proof is a huge thing, and it was done in the middle of the war. It's brilliant. So we will use this analytical result to see how our models work. Okay. So how are we going to solve it? As you can see, if you go from 4 by 4 to 5 by 5, we need 2 to the 25 calculations, right? Already impossible. So what's the solution? Do you need a break? Before we go to the break, let me talk more about Ising model, and then we go to the solution. I'm actually going to ruin it for you, and I'm going to plot it without explaining how this one works. Let me just show it to you. So at low temperatures, two-dimensional Ising model looks like this. Okay, if you wait long enough, at very low temperatures, one of these islands will win. Okay, let me show you. Like if this is 0.1, and let me actually cheat and start from ones. I'm starting from all up, okay, and very low temperature. What will happen is that it will just remain in that very low temperature. All spins are up, and they are happy. I was expecting to get some fluctuations here, but I'm not even getting them. So let me show you a bit more high temperature. Do you see the fluctuations now? Yes? Here and there, fluctuations. So the magnet starts getting demagnetized with increasing temperature. How about when I go to 1.8, for example? More of this stuff, right? Do you understand why this is happening? So as the temperature increases, so let's say I want to flip a spin. How bothered will be the system if the temperature is very low? Very bothered, right? Doesn't want to go there at all. But if the temperature is higher, then here and there it will allow spins to flip. It will be okay. Okay? Just relaxing stuff. It's not fixated on getting to the order. Some of the disorder is good too. Okay. Let's put more temperature to this system. Let's put it 2.1. You might be noticing that there is more disorder now, right? So somewhere at 2.27, there's a critical transition. So let's go above it. And you will see that now, if we wait for long enough, the system will actually lose all its magnetization. The black islands will find each other, and the yellow islands will find each other, and it will be both together. It's better, now we are closer to disorder, so let me start from random initial conditions now. Something like this. Okay? But still, we are not way at the disorder part where you just see the TV static, you know? TV static, like it's black and white, right next to it. It's not like that. There is still some islands of yellow, and within that there are some islands of blue. Within those blue, there are some islands of yellow. Do you see that? Hopefully you do see that. Let me also show you a highly disordered state. This is the TV static. Okay? Now it's just randomness. And this will have zero magnetization. Any questions at this point? No questions at all? So let me draw some pictures. At very low temperatures. No. Let me duplicate this. Very low temperatures, one of the domains wins, the other one is shrunk, right? At very high temperature, no one wins. There are lots of small blue domains, right? Lots of them, and lots of small red domains, but nobody wins, right? Well, at the critical point, actually we have a scale-free system. We have patches of all sizes. So at very low temperature, one giant patch dominates. Very high temperature, several very tiny patches dominate. In the middle, right at the criticality, you have patches of all sizes. Okay? Like you have this, maybe within you have this, you have this. Does it make sense? Actually, there is an interesting thing going on here, something that we call self-similarity. If you take this picture, if you make a very nice high quality calculation of, let's say, 2000 by 2000 and put it here, then just cut a patch out of it, 1000 by 1000, put it here, you wouldn't understand which one is the larger one, which one is the smaller one. You see this in the rocks and stuff like that, right? Like when you look from Google Maps, there is a river, okay? Then you zoom at the branch of that river and put it side by side. It's the same thing, right? That's what happens at critical point. Any other thing that I forgot and you might remind me to talk about? Interesting stuff in Ising model? Okay, let's have a break.